As part of the Quiet Technology Demonstrator 2 project, Boeing had to flight test new technology that they felt would make a difference in reducing the sound generated by their aircraft. Now this is cool, but how they did it is even more interesting. They had an airstrip that was 250 feet wide by 300 feet long, and they retrofitted it with over 600 microphones, and they listened as aircraft flew by. Now they did this 300 times and gathered over 1 terabyte worth of data, and they made noise level maps so they can visualize the kind of sound being generated by these aircraft. Now what's most interesting about this is the program for the project was developed by one person. Now, how do they do that? Now, it's by using the right tools at the right time. And at the core of these tools is LabVIEW. Now, I want to show you how your students can go from taking a quick measurement to solving some grand challenges with LabVIEW. Let's take a look. I want to take a look at some real data. So I'm going to be using a MIDAC plugged into my laptop. And what's cool is when I plug it in, the Elvis instrument launcher opens, and immediately I can start using pre-built executables to see some signals. Now, I have a few ways I can do this, but first, let's create a signal. I can do that using the function generator. In this, we can change the frequency, amplitude, and DC offset of a sine, triangle, and square wave. We can also perform frequency sweeps in more complex cases, but we're going to go ahead and keep it basic for right now. Now the function generator is outputting to the analog out 0 channel, and I have that wired to analog input 0 on my MIDAC. Now before I run it, I want to be able to see what I'm producing, so let's also open a scope. Now I want channel 0 of our scope to have AI0 set as the source. Now I'm going to run them both. Now when I click auto scale on the scope, the signal is set to a default size for amplitude and time. Now I can change the time per division to stretch the view of the signal on the time axis. I can also change the volts per division to stretch the view of the signal on the amplitude axis. Now, this signal is moving around a lot, so I can use a trigger to capture shots of the data at the same point in order to help out. Now, I can change around the signal from the function generator side. I can change that amplitude, I can go ahead and change that frequency, and I can change that DC offset. But this is in the time domain. If I wanted to see the signal in the frequency domain, I can use a dynamic signal analyzer. I'm going to go ahead and run that. Now you can see what happens as I change my function generator signal and its impact on the dynamic signal analyzer. As you can see, as I change the frequency, that spike will move around. Now if I change from a sine to a square wave, we're going to see we get a bunch of harmonics. Now let's take a look at something a little bit more interesting. Remember how Boeing used over 600 microphones in their project? Well, we can start understanding what their application looked like with these virtual instruments. For this, I'm going to go ahead and plug a mic into the audio input channel of my MIDAC. Jumping back to the scope, I can change the source channel to audio input right and start listening to a plane taking off. Now this is great, but what if I wanted to look at this signal and make some decisions from it? Well, I can't do that in the instrument launcher, but these executables were built in LabVIEW, and we have the ability to develop further using LabVIEW. Now I just so happen to have an example that acquires sound data from the mic input on my MIDAC. So let's go ahead and run it and listen again to a plane taking off. Now jumping to the block diagram, we see that there are a few blocks in a while loop so that our code can run continuously, and these blocks configure the channel and timing information of our acquisition. But we're interested in doing some analysis. So let's go ahead and add a filter to our data to look at a specific range of frequencies, then use a power spectrum to see the frequency content of our signal in that range. Then we can toggle a Boolean if any spikes in our frequency range go over a certain value. First, let's make this loop bigger. Now let's go to the Express palette and pin it down. Now let's grab the Filter Express VI and drop it on our block diagram. When I do that, a configuration window opens. Now, I'm okay with most of these settings, but I'm going to go ahead and change the filter type from low pass to band pass. Then I'll change the low and high cutoff frequencies to 500 and 2000 Hertz respectively, and I'll click OK. Now I'll grab the Spectral Measurements Express VI and drop it on my block diagram. Here I'll just choose Power Spectrum and click OK. Next, I'll grab the Statistics Express VI and place that. In its configuration window, I'll select Maximum. Finally, I'll grab a greater than function from the Compare palette. Now, I happen to know that this signal starts to rise past -50 dB throughout the length of the clip, so I'll use that as my comparison value. Now I'll just wire everything together and we'll see how it looks. Now when we run this VI again and play our clip, we see that the Boolean indicator lights up once our frequency power goes above -50 dB. Now we've seen how you can go from taking some really quick measurements to developing some really interesting analysis programs. The next step is up to you, but feel free to challenge your students to solve some really complex problems, knowing that they have the right building blocks. Till next time.